is yours, Oskar.
Thank you, Michał, for the introduction. Thank you for inviting me. It's the first opportunity for me to talk about this paper, and also maybe if there will be time, I will talk about the other paper, which is the surprise. So it's like the unpublished paper yet, but it's the quantum circuit overhead paper, which should be published soon. I mean, as a preprint. So I will start with motivation to study this topic. Then there will be a lengthy introduction, but maybe I will speed it up a bit. And I will move to the heat kernels, which are, I think, they're not in the title. Okay, there's a heat equation in the title, but the point is that we want to study heat kernels. Then I will briefly mention the idea of the proof. I will outline the main results and the applications, and I will summarize and maybe show some future directions. And if there will be time, I will focus on the applications in the quantum circuit overhead, and we'll show you some results. So as we know, epsilon nets and T designs are pretty common in quantum computation information. They are important mainly because of their applications. So for example, like T designs find many applications, starting from randomized benchmarking, process tomography, various protocols of quantum information, efficient measurement strategies, the randomization, decoupling, entanglement detections. There are many applications, obviously. They're also linked with pseudo-random quantum circuits, which finds applications in equilibration of quantum systems, quantum metrology, random bosonic states. Michał has a paper about it, and quantum complexity and information scrambling in black holes. They also have so-called anti-concentration property, which is useful when we want to study, say, rigorously quantum speedups. And both notions, so epsilon nets and T designs, are quantitatively connected, and the quantitative relations between the parameters of epsilon nets, so epsilon, and T designs, so T and delta, they find applications in areas such as non-constructive inverse-free Solovay-Kitaev theorems and random quantum circuits, and in general in quantum complexity. Okay, so the motivation ends with the paper of Michał Oszmaniec, Adam Sapicki, and Michał Theroretical about, where basically they, up to my best knowledge, they studied for the first time rigorously such relations, and they obtained some scaling of T and delta. And also they provided the lower bound on the T scaling of the T design. And in our work, we obtained essentially the same scaling of T, but we improved the scaling of delta. And we achieved so by constructing the polynomial approximations of the Dirac delta using heat kernels. So as we know, because this is more like specialized seminar, so maybe I won't talk too much about obvious things, but it's useful to think of words when considering quantum circuits. So as we think of some alphabet, which is our quantum operations, and the circuit corresponds to words built out of this alphabet. Now the set being, so we can consider longer words, so longer circuits built out of some universal set of gates. And if this set is universal, then we know that for any operation we pick in the group and some epsilon accuracy, some metric, say operator norm or diamond norm. If this set is universal, then at some point, when we keep increasing the length of the circuits, we will hit the epsilon ball, which essentially means that we can approximate arbitrarily, for fixed precision, we can approximate every operation using some finite circuit length. This can be the basis of the notion of quantum complexity of the unitary, which is the smallest length needed to realize the target unitary up to some precision using operations from some fixed set. And then we can think of the gate set efficiency as a global thing, as a supreme over all those like quantum complexities, yes? And if the set is universal, then we know that all these complexities are finite. And in general, like answering this question, like what is the complexity of the unitary, is like those complexity considerations, they are not that easy. So this is the example given by Michał, I think, on during his talk on the Faculty of Physics. So even like, you know, we can have basically some constellations which cause the complexity to drop, although the circuit is very long. Yes, so even if we consider the rotation on a circle, we fix some rotation and we start composing it, then at some point we will be arbitrarily close to the initial point. Yes, so the complexity of such an operation is essentially zero here. But I won't talk about quantum complexity that much. Let me move to what we know. So what can we say about this L as epsilon? So this upper bound on gate set efficiency. Well, we all know Solovay-Kitaev theorem. There are various flavors of Solovay-Kitaev theorem. So this exponent C differs, usually is between 3 plus whatever and 3.97, depending on the proof. But essentially, it tells us that all universal gate sets with inverses are essentially efficient. Yes, and this is the constructive theorem. Recently, it has been improved by Kuperberg. It's surprising that he managed to get 1.44 as the C. And from the other hand, we can calculate the volumes of balls in our group. We know those constants, with explicit constants for unitary group, projective group, special unitary group. And if we use this bound, we can obtain the lower bound on the complexity of this efficiency. I would maybe call this epsilon efficiency of the gate set L as epsilon, which is essentially tells us the lower bound is log 1 over epsilon, and this is swap, and we cannot get anything better. And now I will move to the T-designs. I will briefly recall what T-designs are. So the T-design, unitary T-design on the projective unitary group is the probability measure on such a group which mimics the averaging properties of the Haar measure with respect to the polynomials of degree at most T. And we can denote such a space of homogeneous polynomials of degree T in matrix elements of U and U bar as HT. And basically, such a space is spanned by the entries of the tensor product of U T times tensor U bar T times, which means that every such polynomial can be written as a trace of some matrix and this, say, moment matrix or whatever. And this way we can say that, well, write what the T-design is, so a probability measure which reproduces the Haar averaging properties, but often this measure, we're interested in the case where this measure is discrete. So we have some Dirac measures here, and those Dirac measures are concentrated on our finite discrete set of operations we consider, and then of course, like this integration will change into a sum. It can be also by nu s, I will denote such a measure which is uniform. So it's 1 over number of generators. And then we can define the delta-approximate T-design as a T-design which is like something which is a T-design approximately. So what we mean by that? We mean that there is a discrepancy between the T-moment operator, so-called, for our measure and the T-moment operator for the Haar measure. And this gives us the discrepancy delta. And if this discrepancy is smaller than 1, we say that such a measure is the delta-approximate T-design with delta given by such a operator norm difference. And we can ask if like the supremum over T of such discrepancies is smaller than 1 or not. And also it is related to the notional spectral gap, which is 1 minus this. The global gap is just 1 minus delta nu s.
Sorry, a
Yes?
quick question. Is a spectral gap concerning spectrum of which operator?
This is the difference between, this is the spectral gap of the averaging operator, or the t-moment operator of our measure nu. But
so this is the second largest eigenvalue of this matrix?
yes. But because the first largest eigenvalue, if you want substitute the Haar measure, it will be
Yes.
always 1 because the
Yes,
constant.
sure.
Yeah.
So this is the size of subleading, effectively subleading eigenvalue. Yes?
Exactly, yes. And now the question is if this eigenvalue, the spectrum can have the supremum, like in the closure, yeah, I mean, it can have 1. If we exclude constant functions, it won't have obviously 1, right? And now the question is, if I take the supremum, will I reach 1 or not? And this difference is the spectral gap, yes? If
Okay,
it's...
and the last remark, and if you have exact t design, then what? Then delta is 0.
Yes.
And then spectral gap is 1, and something is wrong here. So maybe this is just the size of second subleading eigenvalue.
It should be yes, maybe something is wrong. Let me see.
Okay, no, I'm not sure. I don't know, but somehow it looks to me that if delta is equal to 0, then what will be the second subleading eigenvalue?
Yes, it should be. Yes, because delta being 0 is the exact t design.
Yes.
And the gap cannot be
1. Well, could be. Okay, let's discuss it later. So anyway, this is a question mark here from my side.
Right. Okay. Let's go to back a bit later. But anyway, having this, if this spectral gap exists, so if it's larger than 0, which is equivalent to delta being smaller than 1, then we can upper bound the complexity using like log 1 over epsilon term, but with the prefactor which large is determined by this gap, the global gap. So if our gate sets have the global gap, then it implies the optimal scaling. And we know some examples of gates. For example, we know due to work with from many works that when our set is made of gates of algebraic entries, then they have gaps. It is conjectured that a gap exists for any universal gate set. And examples of efficient single qubit gate set are known, where by efficient I mean that they have this delta being this optimal one. So this optimal value of, so the value of delta is upper bounded by the optimal value here. I mean, this is for the generators which are free. Then this is true that this optimal value is like that. It can be also shown for, yeah, some other cases, but essentially it was shown for the like free group by Kesten. This is like related to so-called Kesten-McKay measure, or yeah. Okay. So
Oskar, can I have a question?
Yes.
So I guess you implicitly assume that like this averaging operator is Hermitian or like symmetric?
I don't need that.
Because like when you say about the gap, when you define the gap as like this difference, right? So you might start to have like, I don't know, some problems when you okay. So my question was like this result about optimality of the gap is independent whether you have inverses or not in your.
Yes, you can also show it for some. We can have a version for in a case where your S is not inverse closed. It is in the paper made by Adam and Piotr. You can see
And
like
so,
some other variants as well there.
So, and can you be,
And
I
then,
don't know,
sorry, and then it is
more
understood
efficient
as
when you don't have inverses? I don't know.
when I don't have inverses, then it is not Hermitian, so I understand it as the singular value, as singular values.
Okay.
So square root of t times t conjugate. Okay, and then it's like the measure, not the spectral measure, but like kind of like a measure on the singular values.
Okay.
Okay, there is also another way to think about it instead of t moment. Okay, I won't maybe talk about it, but there is also another way to think of instead of t moment operators, we can consider like averaging operators. So we think of the square integrable functions on a group, and we consider like we are moving this function according to our fixed set of elements or integrate over our measure. And then we will get this deviation, this delta here, which is given by these operators, is the same as the previous delta. And more generally, maybe it's good to know that you can have the generalization of the Fourier analysis on compact groups. So we probably many people know Peter Weil theorem, which is for compact groups, and it tells us that pro-integrable functions, they can be decomposed into, it decomposes into like or irreps, and it also gives us some orthonormal basis here. And we can define like via Bochner integration of such irreps with respect to them, like some measure. We can define the Fourier transform of a measure, but maybe it's more useful to think of functions. So if our like measure is regular enough, for example, via means of like Gladon-Nikodym derivatives, we can think of functions or densities, and then we will have like some like isomorphism of two Hilbert spaces, Hilbert space of square integrable functions and Hilbert space of like endomorphisms of our representation spaces equipped with the Hilbert-Schmidt norm rescaled. Okay, so there is some notion of Fourier transform here and Plancherel theorem and things like that. So, and this is like in fact a generalization. So if you take a torus, one-dimensional torus, then you will reproduce the Fourier transform. Okay, so it is useful to think of this way because then the averaging operator is just this integration with respect to the regular representation, and then you can write things more concisely. And anyway, why I'm talking about this, because now I told you about this global gap, but it's very hard, it's impossible to calculate the global gap. So we want to kind of think of the local gaps. So we want to restrict the representations we take into account. So for example, Vario uses like some scale of the highest weights, but we in our work usually use the weights which correspond to t moment operators. So we look at the basically things which correspond to t designs. So the idea is to restrict our averaging operator to finite dimensional subspace, and then we have an extra parameter here, the scale up to which we calculate the gap, and it's still useful. It still allows us to upper bound the complexity. This formula is rough. It's roughly like this. It's more complicated. And there are some results about the spectral gap decay. So if you combine this result, which is kind of a generalization of Solovay-Kitaev theorem, with the result of Vario, which tells you about the decay of the spectral gap, which is polylogarithmic, you will get something like inverse 3 Solovay-Kitaev theorem. And the problem with this approach is that the constants in such a theorem are unknown, because the constants in the spectral gap decay thing are unknown, especially R0. So the scale up to which I need to calculate the gap is unknown. At least it was not provided in the paper. but all the previous things, except for the spectral gap decay result, that you can make them explicit. So have all the constants known, which is a good thing. Now, okay, I will move now to heat kernels. So we want heat kernels because they are basically.
Sorry, Oskar, can I ask
yes,
about
this is
something?
from your paper.
Yeah, a previous slide. Yeah. So I know that you are sort of working on sort of giving quantitative version of this bound by value. Yeah, like do you have some, let's say, idea like how especially these are zero scales?
I don't have any results, but this is something I want to do. Maybe even after submitting my thesis, I just want to finish this problem.
So some people in quantum computing like have basically conjecture, let's say, for reasonable gate sets in on n qubits, that basically just looking on the fourth on R that corresponds to the fourth moment, okay, or 4 copies of the unitary should suffice, let's say, in a sense.
Yeah, this is something. Yeah, I have also heard of it, but I don't have like the proof or something. I cannot also tell you why I don't think it is possible. Maybe it's the case.
Okay.
But yeah, basically like these moments. Yeah, I think you need to 4th or 6th moment to determine if the set is universal, and this maybe it makes sense to look at 4th or 6th moment, depending if you look at d equal 2 or more than 2, right? It's all in the paper of Michał and Adam and Lorenzo about universality.
And Zoltan.
And Zoltan, yeah, Zoltan I saw that later, yes, but yeah. So yeah, this is like a maybe reasonable answer, but I don't know. I don't have a proof of that.
Sure.
Okay, so why we want heat kernels? Basically, the idea is that we want some kind of approximate identities, and maybe it will be clear later why we need approximate identities. So, approximate identities you can think of is like just like some family of functions which behave like Dirac delta in the like. So they integrate to 1, and as our parameter approaches, say, 0 or infinity, it just depends on like what we like. Our function is kind of like the support kind of the integral outside the ball, it vanishes. Yes. So and like the heat kernel is kind of a natural thing you can try to use as such an approximate identity. So we all know like the heat kernel on RD, but you can have like the heat equation. You can write it on any, like, say, Riemannian manifold by means of Laplace-Beltrami operator. And well, maybe I don't have time to go through this example, but in the paper, like that you can try to solve like the heat equation on a circle by using the Fourier transform, and then calculating the inverse. You will get the fundamental solution, which is on R, and then you can, for example, periodize it to get the solution on a circle and apply Poisson summation formula, which will give you like the solution in the form of a complex Fourier series, which can be written into a cosine sine form, and then you see something everyone knows when he was solving like heat equation using Fourier series. But this is like a bit different way to solve it, because it uses Fourier transform and periodization and Poisson summation formula. Anyway, like this thing is like consists of eigenfunctions of the Laplacian multiplied by e2 minus square of the eigenvalue, right? And now I'm just recalling it because now I want to do something similar on the on a group, yes, say on and now how can we do it? Basically, like the universal enveloping algebra corresponds to left invariant differential operators on the group. And this is not surprising. Well, we are using that, and basically to look at the spectrum of the Laplacian or eigenfunctions, eigenvalues of the Laplacian on a group, we can have a look at the Casimir elements instead. So the Casimir element is just is given for Lie algebra of fixed basis. It does not depend on the basis, but it depends on the bilinear form which is picked, because we need to use that to define the dual elements which are here, right? And then I can have a look at the right, like the differential of this representation and the image of this element. And it turns out that this is identity times some basically the eigenvalue. And you can calculate this eigenvalue, and the eigenfunctions are of the Laplacian on a group are basically the matrix elements of irreducible representations. In particular, like the action of the Laplacian on the character will be, the character is the eigenfunction as well, with the value, eigenvalue determined by the weight. Okay, and then you can basically arrive with the heat kernel on a compact simply connected semi-simple Lie group, say SUG, and here we assume that we take the metric induced by the Killing form, because this is like the natural metric you can use in this scenario. And we arrive with the heat kernel. And what's nice about this formula is that we can bound the dimension using, like, say, Weil dimension formula, and we can bound also the k's which are in the exponent. And here's sigma. So normally in the heat kernel scenario, this is differential equation with respect to time. Here, of course, we don't have any physical thing going on, but so we substitute time with the sigma parameter, which kind of like plays the role of time here. So when sigma is 0, we approach 0, we approach the like Dirac delta solution of the yes. But the core thing is that we can bound upper bound D and lower bound K. So basically we can bound the things which are in the heat kernel. And now, because we want to have the polynomial approximation, we can trim it. And if we do it like in a brutal way, it seems a bit arbitrary, but in fact, such a brutal trimming is optimal in a sense that this is you can easily see it from, say, Hilbert's projection theorem, yes. And basically, this is like the closest object to the full heat kernel in the L2 norm. So
can I ask something?
Yes.
So what's the relation between the length of lambda and the degree of design?
The length of lambda. So the degree of design, it's just upper bounds the one norm of lambda.
Mm-hmm. So the degree is t.
Yes.
I see.
This is like the trimmed to HT basically right now. This heat kernel.
And can I ask? So this bound on the dimension. Let's say it's nice, but like, do you know? Sorry for like it's like because for other reasons I was looking on related things recently, like let's say to what how to put it? To what extent it's tight? Basically, that's my question. Yeah, cause okay, maybe it's like technical thing. We can maybe discuss it later, but
I can maybe very quickly answer that question since I think I proved this formula 25. So there are lambdas for which this is tight, but for most it is wildly not tight. Okay, but there are some examples for which this is equality, I think.
And how so in terms of Young diagrams, how they look like?
I don't know.
Okay, thanks.
Sorry.
Also, we don't use Young diagrams here. This is usually what you do when you consider irreps of SUD. You look at Young diagrams. But here we think of lambdas as just the weights of the unitary group, and we think of E-reps of SUD as some restrictions of the ones which are from the unitary group. So it's just like, yeah, just a technical thing. Anyway, like the point is that we can now try to construct the corresponding kernels on projective unitary group. And okay, before I go to that, there is like a technical thing that I have also the Poisson form for compact semi-simple simply connected Lie group of the Heat kernel, which was given by Urakawa. But the point is that it only works for semi-simple groups, and projective unitary group is not a semi-simple, so we just need to do something about it. And why we want to use the Poisson form? Because it is essentially useful when we want to consider small sigma. So when we are close to the like this delta Dirac delta thing, whereas the character form is good when sigma is large. And okay, so I don't maybe not want to waste time on that, but basically the answer is if you want to have the heat kernel PUD, you can just average your heat kernel SUD using like the center. Okay, ZD, just do the shifts and average it. So this is like similar, like if you do something like that to the character of SU2, then you will get that basically like the full integer E-reps are also the E-reps of SO3, so projective group, but the half integer things are not. Okay, the character will average to 0 basically. Okay, so now going back to this proof idea, we kind of have some approximate identity. I didn't prove it is an approximate identity, but this is what we do in the paper. And now what can I do? How can I like, this is like again, the image from Michal's paper and Adam's paper and Michał Holodecki's paper, which was like before. So the idea is the same basically, yes. But maybe I'll recall it because not everyone knows it. So if we assume that our measure or our points, yes, they are not an epsilon net, and we pick an element outside, so we know it's like epsilon separated from another points. Yes. Now if our measure is a T design, then this HT is a heat kernel, but it's basically whatever approximate identity we use. Okay. We need approximate identity to be in this polynomials, in this HT, okay? That's important. If we know that, then we know that the average, the integral over a ball around this point, which is separated, of the spread out, we are using the average operator onto this, peak. It spreads it out over all points. We integrate it over a ball which is outside, yes, this green ball. If HT is in HT, sorry for the notation, then we know that the average is to the volume of the ball. But on the other hand, as sigma goes to 0, so our things are getting more and more peaked, and the integral needs to go to 0 because like the integral outside of all of these balls goes to 0. Yes, that's the idea how to prove by contradiction, like. For example, what is the T needed for something to be an epsilon net? Yes. So the idea of our proof is that we train the full heat kernel to obtain approximation of, to get this balanced polynomial thing. We prove that it's an approximation of the Dirac delta. We combine the bounds to get the theorem. And we also need to derive the bounds on the L2 norm, and this is needed because in the delta approximate case, this equation 34 is not equality, but for delta approximate designs, this is like roughly true, and how we are off depends on the 2 norm of the function we are using as the approximate identity. So we need to have bounds on the 2 norm of our approximate identity too. So the results. Main results, so the first is like obviously technical things. So we have kind of, in a sense, a new class of approximate identities which are polynomial, and they come from Dirac delta function or projective unitary group. And we know like the properties. So we know how fast how fast the 2 norm changes. how fast the interval outside the ball vanishes and things like that. Yes, so we have the characterization of this. And the theorem we proved is, as if in the more general case of delta approximate things, is that approximate T designs in PUD are epsilon nets for T being larger than, well, this scaling and delta being smaller than this scaling. Of course, we have explicit formulas for T and delta, but here I'm just providing like how it scales, how this formula scale. But we have explicit formulas, and now in terms of the applications, so I already mentioned inverse-free Solovay-Kitaev theorem. So this is something what you get when you plug the various results about the vanishing of the gap to the say Solovay-Kitaev like theorem with finite gap. There might be more. Another application is about to another of Michal's papers. So in this paper, saturation recurrence of quantum complexity random local quantum circuits, the results about this correspondence between delta approximate designs and epsilon nets were used to prove some things about the saturation and recurrence results. So if you are interested, you can check this paper. It is not necessary, as far as I understand. It is necessary if we don't assume the gap, right, of the gate sets. Okay, and final application, like kind of obvious, is the efficiency of universal of quantum gates. So we can basically have the Solovay-Kitaev like theorem with this. Basically, which depends on the value of 1 over delta. Yes, and this is important application because it can be used to bound, for example, the overhead of quantum circuits. And the overhead of quantum circuits is the notion which we introduced with Adam and Piotr in our other paper. And if there will be time and if that will be interesting, then I can talk about this overhead. Let me now maybe summarize this talk, and if there will be need, I will answer questions, maybe talk about this overhead and clarify things which are not clear. So we have improved on the state of the art for constructing epsilon nets in the group of unitary channels from unitary TDs. I didn't say it, but like the unitary channels, they correspond to projective unitary group. Okay. So sometimes I will say projective unitary groups, sometimes we say unitary channels. So sorry about that. The construction is based on the approximations to the Dirac delta based on the trimmed heat kernels, which is a natural object. The construction can be applied to the estimation of the efficiency of quantum gates. Our construction can possibly be used to improve on the saturation and recurrence results for the complexity of random quantum circuits. So this is what's in Michal's paper. And in terms of the future work, maybe there are like 3 things. So first is, can we obviously improve the data scaling even further, or prove that no improvements are possible, for example, by showing the upper bound? So we know the lower bound on T, yes, because we lower bound T and upper bound delta. Yeah. And now we know the best possible T, which is this scaling. Okay, maybe I won't go to the first slide, but we basically know what the best possible scaling of T is. It's just not proved, but we don't know what is the best possible scaling of delta. So we got some improvement, but we don't know how far we can go. And of course, the second question is, can the T scaling be saturated? Initially, we thought that we saturated the scaling, but it turned out that there was an error in our paper and we didn't saturate it. Or maybe there is another error and we saturated it, I'm not sure. But officially, like, we didn't saturate it because there was some error which changed the scaling, which is now essentially the same scaling of T as it was. And now the most interesting, I think, question here is, what are the constants A and B in the inverse-free Solovay-Kitaev theorem, which is equivalent to asking to finding the constants for the spectral gap decay, so R0 especially, because, yeah. So this is the most interesting question. And I think that maybe heat kernels can be used to address this, Because, for example, if you have a look at the various paper, he is using some function which is called chi-r. Not one-to-one, he's not exactly using it, but he's using it to construct some other functions by multiplying this function with some kind of localization. I mean, not in the strict sense of localization, meaning from algebraic geometry, but like the localization in some sense, like, okay. And basically, if you have a look at his function, he doesn't say it anywhere, but if you take the Feijel kernel, not the heat kernel, but the Feijel kernel for SU2, you can prove that it is basically what Varyu has. Up to like a tiny change in the normalization, it is exactly what he uses in his proof. And I don't think that's a coincidence. And basically, I'm not sure what are the generalizations of the Feijel kernel to higher dimensions, but I will say that the most natural generalization would be exactly what Varyu has as his function. And we know that, on the other hand, that kind of Feijel kernels are worse than heat kernels from our considerations here. So maybe it makes sense to use heat kernels instead and try to prove something like the spectral gap decay using that, but I'm not sure if it is a good idea because it depends on some technical details of why Varyu chose this and not other form of this function. But this is like some idea. And okay, and that's everything I wanted to say, unless you want to know something more about this, the quantum circuit overhead.
Thank you, Oskar, for the very nice talk. Yes, so I guess we are not constrained by anything. So maybe like let's just start with like if somebody has a question, just unmute yourself and yeah.
So I would start with a kind of naive question. So look, we know that random matrices, unitary matrices distributed according to the Haar measure. In a sense, they also provide some kind of approximation. They also provide some epsilon t design, yes?
You mean the random gates?
Yes. Well, okay. You have a sampling of random gates. Of course, they do not. Okay, now I say random unitaries. Of course, it's not a t design, but in some sense, it is, I would say, kind of approximation. So my question is, if we use this random set of, let's say, m random gates as a reference point, is it fair to say how much your designs are better than choosing randomly without any, intuition or investing any knowledge?
So there is a paper about random t design. So basically, like picking the generators randomly,
exactly.
according to the Haar measure.
Yes.
And like, what is the probability that they will form approximate t design with given delta? So this is the paper of Adam and Piotr Dulian.
Yeah. So I was thinking one can use this as a kind of benchmark or reference to say how much your approach is much better than using them randomly.
Right. I don't construct any designs, right? I just show like what is the relation between epsilon and delta and t, sorry, and delta.
Yes, right? yes, sure. But then somehow, if somebody would really like to make use of it and construct something, I would like to have some additional motivation why such an approach will be more efficient than doing it randomly.
I mean, or maybe just translating the question like this, maybe picking gates at random according to Piotr and Adam's prescription would give you some, maybe eventually would give you some on one end t designs, on the other end it will give you epsilon nets, right? And like, do I understand your question kind of well? Like maybe like one would then compare the bounds of here compared to.
Okay, so I don't know what are the bounds which come from their paper. I know they give like some probabilities of like getting given delta. Like how many times you need, how many samples you need to draw to to like get with like high chance like a delta approximated design.
Yeah. No. So from my perspective, it is good to use it as a reference point to show how your method gives better result than doing it randomly. Of course, it should give much better results.
Sure. Okay. That's yeah. Thank you for this idea. Maybe I should have a look.
Maybe your co-authors would know more.
Yeah, I mean, for sure, Adam will know more about it.
Okay.
So.
Okay. Some other questions or comments to Oskar. Okay, I have one question, like sort of technical one. Let's say, yeah, like I guess you skipped like a lot of like guts of the analysis or details of the analysis, but let's say fundamentally, what is like? Is there a way to explain like fundamentally what is the reason that you get this? Yeah, like the let's say bad scaling with D, as we had in our previous paper. Yeah, is it related to those bounds for dimensions of the E-reps? Yeah.
So, yeah, so basically like the scaling of T, it comes from these bounds, right? So the scaling, the bound on K and the bound on D, they, as far as I remember, they are kind of the most important things here. And we initially we got better T scaling because we had an error in 26 and we didn't have 1 over D squared in the denominator.
I see. So perhaps if you had better bounds somehow, then maybe it's a better actually. Maybe you can have better scaling.
But yeah, Oliver.
So I'm happy for Oskar to give his perspective. My perspective is that I spent a lot of time staring at these bands. They're certainly not tight, but I think they the bands 25 and 26 essentially are like the correct polynomial order, essentially. This 1 over D squared in 26, and this D, let's say D squared over 2 in 25 are correct, even if the constants and lower order terms are wrong. And essentially nothing else really matters for the final scaling of T with D. Yeah. So you can make these inequalities tighter, but it won't change our final result, essentially.
I see.
I believe.
Essentially, like 26, I think it's kind of state of the art in a sense of it's what we will get from literature, I think. Actually, it was our sin and our fault to use a book initially because it precisely gave us this wrong scaling because there was no 1 over D squared in the book. But this is because of some small details.
Like different normalizations of Laplacians and stuff.
Yeah, so it depends also, like some people normalize scaling form and some people don't normalize scaling form, right? And I think, and also like this, I think that the example from the book was for the unitary group. So 25 is the same, but anyway, like we derived it ourselves and we got 1 over D squared in the denominator. But yeah, it's possible that there is some error somewhere always, which can turn out that like, but we checked it like many times and we couldn't find any like important error in. So probably it is what it is.
Right. Any other questions to Oskar or Oliver?
Can I make a quick comment?
Please.
just about the summary that Oskar gave at the end. So we're not sure, well, I'm not sure whether the heat kernel is a particularly optimal thing to choose, or these trimmed heat kernels are a very optimal thing to use in this setting. But what is true is that they're really easy to do calculations with. So in Adam and Michał's paper, and also in this paper of Ariu, there are some quite technical and difficult calculations you have to do. You have to do some annoying integrals. And if you use the heat kernel, a lot of these technical things that you have to compute just kind of go away. And you just say, Peter-Weyl theorem or whatever just solves the problem for you. So this is why we're kind of excited that we could maybe apply this in the future work, especially to find these constants A and B that Oskar points out here, because we have quite powerful tools for computing things based on the heat kernel that we just don't have if you use something else.
Nice.
Yeah, and also like we don't know if they are like optimal or not, but my intuition is that they might be, at least in a, for example, like basically what Ariu did, as I mentioned, is kind of in some sense using like Feijel kernel, and we obtained a much worse bounce from Feijel kernel than from heat kernel for SU2. So I don't know, it's like of course it's not a proof and whatever, and maybe it's not obvious how this problem relates to other problem, but it's just a hint that maybe heat kernel can give something, do something better.
Sure. Nice. Okay, I guess, yeah. Okay, let's say it's a last chance to ask something to either Oliver or Oskar. Yeah. So maybe just maybe very briefly, can you just mention what you mean by this circuit overhead? Just like how?
Yeah, so basically like what we did is in other paper that we introduced like this quantum circuit overhead, which is basically like how longer the circuit is, this LS epsilon is compared to like the optimal possible gate set with given number of gates, which of course this overhead cannot be calculated because we cannot access this, but we can upper bound it. And by some quantity which is easily calculable, and we actually calculated it. Also, you can make a version of it which kind of focuses on like number of T gates or something. So in a setting where you have like a finite group plus some group, some extra gate which makes it universal, yes. And basically, what is interesting is basically why we are doing that. Why can't we just use L? Because it depends on the number of generators, yes. And it's not like adding generators is mathematically neutral operation, but in practice, like the more gates we have, the harder it is to build something. So it makes sense to like consider like this LS epsilon for gates which have some, say, fixed number of elements. And in this sense, like it's just like dividing it by some here, like the kind of volumetric bound. And what's interesting is that we checked it for Clifford group and for Hurwitz group, and we obtained that, for example, that the T gate is very not unoptimal in this metric in terms of the upper bound on its overhead. And we found like a gate which is also of order 8, which is close to being optimal. But the value of this Qt for the T gate is 52, so it's totally outside of the scope of this this image. So in this sense, like the upper bound on the overhead of the T gate is huge. It's an outlier, which is kind of interesting. Of course, it's an upper bound, so it doesn't prove that this overhead is bad, but it's interesting. So yeah. Yeah, this is basically like the and why maybe just one sentence. How do we apply this result here? Basically, we need to know what is the scale needed. So this T of epsilon in 41, we need to know what the T of epsilon is, and this T of epsilon is given by this bound from the construction. But in practice, it's like, of course, it's just a bound on T. So in practice, it turns out that the probability densities, they stabilize quite fast. So if for 500, for 1 qubit, there's not a huge difference between 50 and 500. Yeah. So from just like a takeaway thing is that you can calculate, you don't need to use like T's from these bounds. In practice, much smaller T's are sufficient because, of course, those things are just some bounds, usually not very tight.
So here you plot those results for SU2 only.
Yeah, for PU2.
Right. Right. So but like let's say, so you view this T gate as like some extra gate on the top of single qubit Cliffords, right? But like what if you had it as just embedded in 2 qubit scenario?
For 2 qubit scenario, yeah, this is something which we won't maybe can do in the future. Basically, I think we picked this scenario because this is we also checking so-called super golden gates, and this is like a paper by Sarnak about super golden gates. He introduced super golden gates, and I'm not sure if we can easily make this TQCO work for more than 1 qubit. Let me think. Probably we can do the same thing, yes, because if I have like a 2 qubit gate set, then I can still describe it as a like finite group plus some extra gate, right? Maybe 2.
Right.
So probably, yeah, you can kind of like still make sense of this TQCO for 2 qubits. Yes.
Right. Thanks, Oskar. Okay. So many thanks again for a very nice talk and presentation of your results.